Welcome back. This will be an example of how to use Spider or Python to solve first order ordinary differential equations as part of the lecture notes for Phys 2500 at the University of Windsor. I'm Dr. Hammond. So as we just went through in the previous slides that I've now also uploaded to Blackboard, you can follow through how to find the analytic solution, and I make a few little notes on how to set up these algorithms for solving this first order ordinary differential equation. This time we'll actually be going through the Python code, and I'll be using Spider to run it. I like the Spider environment, as I mentioned before. It's kind of environment I'm familiar with, and you can see how all your code, it compiles nicely. It spits out any errors that you may have, and also you can see all your variables, and so if you want to make sure that things are being passed the way that you think that they are, they can come up in this environment over here in the variable explorer. Okay. So again, when we set up our code, we have to import the packages that we'll need. So we import matplotlib.pyplot, but we don't want to type this every single time we're trying to plot something, so we can just make it short, kind of create a shorthand for it, and you import it as plt. Also, we'll want the numerical package, and so we'll import numpy as np. And I'll be discussing the built-in solver from the scientific package integrator library, and so we'll use the ODEint built-in solver. And again, I like to close all my files at the beginning, or all my open windows and plots at the beginning, so I use plt.close and then quotation all. And so that way it just kind of keeps my desktop a little bit cleaner. Sometimes if I'm worried about something taking too long, I'll also import time, and then you can see when your algorithm starts at time.time, and then if you want to see how long it takes at any point, you just call timer start at time.time, and then you take the difference of the two, and that'll tell you how long it takes for your algorithm to work. You can also do debugging routines that can do this too, but I kind of like just doing this because you can easily put this wherever you need. Okay. So as I mentioned previously, if you use through the hashtag or the number sign and then percentage sign, you can use this to break different sections. And the benefit for that is if you hit Shift Enter or Control Enter, you can just run a small section of your code if you're just trying to like debug a certain part or something like that. I like using it because it kind of breaks it up, so I can set up different parts of my code for different purposes. So at the beginning, I'm just trying to define everything. So we're going to have some initial velocity. I'm going to say this has 108 kilometers per hour is our initial velocity. I think that works out to something, is that 70 miles an hour? Maybe something like that. We of course want this to work in meters per second, since we're all familiar with SI units. So I convert this from kilometers per hour to 1,000 meters per hour, and then divide by 3,600 seconds per hour. And so we can convert this from kilometers per hour to meters per second. We'll give some drag coefficient. It doesn't matter what this is. So I call this 20 times 10 to the minus 1. I don't know why I wrote it that way, but you can put it however you want. This works on the kind of the time window that we'll be using. So I'm just integrating over 5 seconds, but if you want to have longer, you can have a smaller drag coefficient. If you remember from our curling rock example, I think it was like the first assignment you guys had to do for this course, the rock moved for 22 seconds or so, and the drag coefficient was, I think, 0.16 or something like that. So you can change it as you want, but you'll have to change your time that you're interested in integrating over as well. And then, because we're in SI units, acceleration due to gravity is 9.81 meters per second squared. So we'll just keep that here. NT, again, is our number of steps. It has to be an integer because we put that in here. So as I mentioned previously, if we wrote 20 here, as in 2, 0, and nothing else, this is automatically, that would be an integer value. But writing in scientific notation of 2e1 makes it actually a floating number, and so you can't pass that into this linspace. And so what you need to do is define it as an integer. Same thing as if you called it 20.0, you would again need to make that an integer so that linspace can read that value. All right, so t, we just have a linear spaced array from 0 to 5 seconds with 20 values. And dt is just the difference in or any time step in this array, so it's t1 minus t0. I like kind of keeping this all together because eventually I'll show you that we need to change this nt in certain instances in order for our integrators to actually work, or our algorithms to actually work. And so this way, instead of defining dt as some set value, we'll just change it accordingly to however many points we use, and I just find it to be much more efficient. Okay, so we're going to start off with the exact solution for no gravity, and we have drag that is linearly proportional to our velocity. So I define um. So this is actually, um is this mu that I talked about before, the drag coefficient divided by m. So I just kind of lump these things together because they're always together. And so that way we don't have to define the mass, we don't have to define the drag coefficient, we just define the two things together. Okay, so now what you need to do is define your function, so the thing that we want to solve. So we define v dot, so of course v dot is going to be dv by dt, and we're going to need to pass in the time array and the thing that we want to solve for, so velocity. And so what we return is minus um times this velocity, and so this velocity is this function that we're trying to figure out. So this is all you need to do to, in fact, define your derivative. So you just have to return what this first order ordinary differential equation is, so it's actually quite simple. And then I go through here the different integrating routines. So again, we use Euler, as I described in the notes in those slides, that because we have dv by dt is equal to negative times v, that we can actually just say that the next step in v is equal to the current step in v plus dt times dv, dv by dt, I guess. So it's delta t times dv by dt, and so we get v, the next step of velocity, is equal to the current velocity plus this derivative of the velocity, and that is the Euler integration routine. And as I said, this is like a literal translation of what an antiderivative is, but as we'll see, this is actually a really bad algorithm for solving for velocity. So we return the velocity and we get this Euler velocity is what I call v Euler. So this is called Euler because apparently he was the first one to ever think this up. So back in, I think, the 1700s or something like that, he was trying to solve for something that didn't have an obvious analytic solution, and so he actually was trying to do this with pen and paper, or quill and I don't know whatever he was writing on, yeah, actually had to integrate these things by hand, and showed that it actually kind of works. But a far better algorithm is the midpoint algorithm, and as I discussed this in the previous tutorial, that all we need to do is we have the exact same thing that we call it, well, I guess here I use I and here I use count t, but whatever, it doesn't matter, it's just some dummy variable. So we have the next velocity, or the velocity at the next time instance, is our current velocity plus this little dt, this time step, times, and what we do is we have v dot, but if you notice, this v dot actually contains the arguments of our time 1/2 step in the future and our velocity that we have now plus 1/2 time step into the future of what the current velocity is. And so because we have v dot defined in this function, all we need to do is stuff these things that we already know into this v dot function, and it'll return the next velocity. And so we call this v mid for the midpoint velocity. And we can expand on this. So as I said, that just like the midpoint algorithm uses the Euler algorithm as kind of like a first guess, as what you kind of have here. Runge-Kutta uses the Euler algorithm as the first guess, the midpoint as the second guess, and then we have 2 more kind of guesses for the next point, and then it kind of takes an average of the 4. And so we have this K1 is the Euler algorithm, K2 is the midpoint algorithm, K3 would be a different way of calculating that point, and then K4 is basically almost kind of like using algorithm, but at the far point. And we bring in this K1 by 2 and plus K2 by 2 and then plus K3. This is all we need to do for the RK4 algorithm. And we get that the next velocity is the current velocity plus 1/6 of K1 plus 2K2 plus 2K3 plus K4. And this is all that there is to the Runge-Kutta algorithm. This is really nice in Python because we can define these functions and then we can just pass these functions or these variables into these functions as we need to in order to perform this integration. So yeah, I like this. It's really handy with Python. For those of you who might be more familiar with object-oriented programming and stuff like that, maybe you know how to do this in C or C++ and things like that. But I find Python this works quite intuitively. And so we get a velocity with RK4, and we'll just call it V because that's what I just called here. So now we're going to introduce the built-in solver. So for using the built-in solver, I don't think I mentioned it in the slides, that what we need to do is call this library the ODE or the integrate library, and we need to use the function ODEint. So you need to put this somewhere in your code so that we can use this built-in solver. So the built-in solver, you define your function in close to the same way, although as I defined the function here, that it was t comma v. Here I need to define it as v comma t. I'd seen on some forums that you can call it as either t comma v or v comma t. However, maybe that's in different versions of Python. It seems like in my version of Python in 3.7 that I need to define a function as v comma t. If you can find examples of this working the other way, then please let me know. But so far, this is how I've seen it to get it to work. But in the exact same way, all we're returning is the differential equation. So just like what we had here, that we define v dot as negative mu or um times v, we again are defining our function and we're returning this derivative. So it works the exact same way. But when we when we try and solve it, we just use this ODEint built-in solver. You pass in your function, and then you put in your initial conditions and your time. And this is, to my understanding, this is why we have to pass this in as velocity and time. It's because we pass in the initial condition and then the variable that we want to integrate over. And that seems to be how the built-in solver works. If you want to, you can also call this as a parameter. There's really no difference between just defining this as some value earlier on, or if you pass this in as a parameter that you can change later. I guess it's just whether or not you want this to be like a global variable or not. But in any case, this is what you do. So your answer ends up being using this ODEint built-in function, integrating over your returned function with some initial value and the array that you're trying to integrate over. And then we'll call the velocity of the built-in solver as the zeroth element, or I guess the first column of our P sol, which is our solution. All right, and then we plot it. So I'm plotting in black the exact solution, the Euler integral in red, the midpoint integral in blue, the RK4 solution in green, and the built-in solver in magenta. I also put these in different line widths so that if you wanted to see, because a lot of these will lay right over top of each other, I have them with different thicknesses so we can actually see, one on top of the other. And then of course you need to label your x-axis, your y-axis, and give it a title so you know what you're doing. And so let's see what happens when we run this. So keep in mind that we're using 20 data points or 20 time steps to solve this. And what we get is exactly what we expect, that we have the exact solution goes as an exponential decay to 0. This Euler solution looks okay. It also decays. Whether that's exactly an exponential or not, I don't know. It seems to decay a little too fast, but it comes to the same value that it ends up going to 0. But you can see that the midpoint is in blue, and that's well overlapped with RK4, which you can't even see because it's completely overlapped with the built-in solver. So if we zoom in very closely here, you can see that, well, that you have the midpoint that's a little bit off, and then you have the RK4 and built-in that are very close to one another. So we zoom in very, very closely, you can see that there is a slight difference between our RK4 answer and the built-in solver, but you can see the built-in solver actually ends up just agreeing exactly, basically to kind of any arbitrary zoom in. I guess you can see at very, very fine resolution that there is a slight difference between the two, but it's not very much. And of course, if we had fewer time steps, this would be faster to calculate, but you would see that there'd be an even greater difference. So you can see that Euler actually kind of overshoots, so somehow it goes into negative velocity before it settles on 0. You can see even midpoint with so few time steps that midpoint even starts to have a fairly large error. But RK4 and the built-in actually still agree quite well. So this is only for 10 points over 5 seconds, so this is actually quite large steps. But if we say integrate, say 1,000 steps, you should see that they basically all agree. And now, up to this kind of zoomed out precision, they're actually agreeing quite well. So in this case, this is quite simple. We're only integrating 1,000 steps, so it's not too difficult to get all of these routines to work. Okay, so that was for the first instance. Now I'm going to change this so we can just hit Control-1, and then that way we can comment that out, or we can go to Edit and then Comment and Uncomment, and we can comment out something. If you want to uncomment a bunch of things, you can just select it all and hit Control-1, or select all and hit Control-1 to comment back out. So we're going to use the inhomogeneous differential equation with linear drag, and so now we need to also change this built-in solver, and I need to change the exact solution here. And so running this, what did I change? Oh, right. I also need to change this to have no initial velocity. So with no initial velocity, we've now dropped this ball. This thing is falling in the air. And what we can see is that we now have this exponential decay to some terminal velocity. So they all reach the same thing. It's all 5 and or close to 5. And so that's because it's um over g, g over is the terminal velocity. And so these things all exponentially reach that, but Euler again is kind of off. Nothing's really changed from the two. But if we go to this nonlinear drag case, and so let's also change the exact solution, and now we need to have an initial velocity, and I'll need to change this. Notice that when you want to square something, it's times. So if you want something to be, to the third power, it's times 3, or square root would be times 1/2. I'd recommend putting 1/2 in brackets just to make sure that things aren't saying like times 1 and then the whole thing divided by 2. Just to make sure that the order of operations is how you think it should be. Okay, so now working on this nonlinear drag coefficient case, and we have an initial velocity, so this should work. And you can actually see that I got some error here, overflow encountered. And so then if we look at our plot, we can actually see that Euler has just exploded. So everything looks really, really small. Everything's basically saying 0, but Euler, for some reason, has exploded to some ridiculously large, I guess, negative value. So Euler has actually, it doesn't solve this. And so if we increase the number of steps to, say, 2,000, then we get, what did I do? Oh, I don't have that. So now you can see that if we have 2,000 steps, that they all agree fairly well that this, at high velocity, because it goes to velocity squared, this drag goes to velocity squared. At high velocity, this thing slows down very quickly, and then once we reach slow velocities, this drag is actually quite minimal. And they all agree. But I want to emphasize that, yeah, if we only have, say, a few points, this Euler integration routine actually explodes. It actually doesn't find a solution. It doesn't converge. And this is actually something you really have to really watch out for when you're on these routines. Is you have to make sure that these answers actually kind of make sense, because if you don't have enough time steps, this can happen, particularly with the Euler routine. Some integrators are inherently stable. So if you're solving, say, for example, instead of ordinary differential equations, partial differential equations, then you can use what's called the Crank-Nicholson integration routine. That integrator is always stable, which is really nice because you'll never get your answer to blow up. But the problem is that if you don't have enough integrating points, it might be giving you garbage and you don't recognize that it's garbage. So you kind of, when you're running these things, you kind of want to increase your number of time steps by, say, some factor, like say a factor of 2 or an order of magnitude. And then you say, oh, okay, if we've increased this from 20 to 200, we see that Euler still explodes. And if we increase, from 200 to 2000, we see that Euler actually solves something. So if you're using the Euler integration routine, or if you're using any integration routine and you want to make sure that it's actually working or it's converging, I'd recommend that what you do is you have a number of time steps that you see an answer that you think seems plausible, and then you increase those number of steps by some factor, say like a factor of 4 or something like that. And then we say, well, if it worked at 2,000, do we get the exact same solution at 8,000? And you say, oh yeah, it does. And so that way you can it kind of ensures, or kind of is like a first order test to make sure that what your answer is doing is kind of consistent. Because if you increase the number of points, or say you don't have enough points, like what we had, for Euler, and you'd say, if only you used Euler here and you saw that this answer goes up to, 1 times 10 to the 292, you would say, hey, I just discovered that if you have nonlinear drag, that you can go faster than the speed of light. Obviously, that conclusion is incorrect. So what you should say is, okay, well, I'm going to increase this by an order of magnitude and say, oh, this actually reaches, something that seemed kind of plausible. And then if you increase this by another order of magnitude, of course it takes an order of magnitude longer to run, but you get the exact same answer. And with that, you can be a little bit more confident that the answer that you're getting is a good answer. Okay, and the last thing I want to talk about is using this for something that we don't have an analytic solution for. So I'll just give my analytic solution, I'll just have it times 0. But if we have some source terms, we have gravity, and then we also have nonlinear drag. So we can use the solvers that we've designed ourselves, or this built-in solver, to find how these things work, and we'll actually have no initial velocity, and then we'll see what these look like. And so we said that our exact solution is 0 because we don't know what that exact solution is. But this solution ends up looking something kind of like what we had before, where this reaches some terminal velocity, and this ends up having that kind of that curve that we saw before that goes as 1 over t, and then reaches this terminal velocity. So we can use these things, these solvers, for something that's more complicated, of course. So something that doesn't have an analytic solution would be if we call this 1.5, and we could do that with our built-in solver as well. I mean, we could have this like 1 point, we can have this at some arbitrary value, which you can't really do, you know, analytically for some arbitrary function. We could even make this function, you know, a power series of velocities and things like that. So that's the nice thing with solving with using these numerical integrators, is basically all we need to do is change our return function to whatever we want it to be, and this thing can be arbitrarily complicated, and we can always solve these things. As opposed to when you're doing an analytic expression, you kind of, as we saw the difference between either the homogeneous and the inhomogeneous case, that we actually had to do, you know, substitution of variables and then figure out this integral and all this kind of stuff. For this, all we need to do is change the numbers as we want. So this will conclude these lectures on how to solve first order differential equations. Please go through this code and practice it to understand, or, you know, read it over a few times and use it a couple of times to see how to do it. Maybe change these return functions to see how you can solve other first order differential equations, so that you get a little bit of experience with it, because for the tutorial on Friday, I will want you to hand in your code for how to solve different terminal velocities for different conditions. So I'll be showing you how to use the built-in solver, and then I'll want you to use your own solver. So either midpoint or RK4. I highly recommend against using Euler, but one of your own algorithms to find the terminal velocity for, or the velocity as a function of time, or position as a function of velocity and position as a function of time, of an object that's falling from, say, the International Space Station. So something that's 150 kilometers up in the sky. Say somebody drops a wrench or something like that out of the International Space Station, and this thing falls to Earth. What I want you to calculate is the velocity and position as a function of time, and even the acceleration as a function of time as this thing's falling through the air, when you have no atmosphere, when you have a constant atmosphere, when you have an atmosphere that varies as a function of height, and even when you have gravity that varies as a function of height. And as I said, you'll be able to easily do this with these numerical solvers, and this is what I want you to try and do. All right, so until Friday, good luck working with these codes, and I'll see you then.